Hello there, and welcome to the Sleepy Science Channel. Tonight, we'll be drifting into the great unknown. Space is a vast and endless expanse, full of wonder and mystery. It contains ancient galaxies we can't explain, forces that bend our understanding of reality, and questions that still remain unsolved. Beyond our familiar stars lies a universe filled with hidden matter, unseen energies, and events so powerful they ripple space-time itself. This is a place where time behaves strangely, where distances stretch beyond instinct, and where every answer opens the door to another mystery. After centuries of scientific progress, our understanding has deepened, yet certainty always remains just out of reach. From the earliest moments after the universe began to its many possible futures, space invites curiosity without ever fully revealing its hand. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. Let your body soften and allow your breathing to slow. And allow the day to gently fade away as we explore the mysteries of space together. Let's begin. Dark energy is speeding up the universe, and we do not know why. For a long time, expansion seemed like it should slow down under gravity. Then distant, exploding stars were measured as if they were farther away than expected. The simplest reading is startling. Expansion is accelerating. Something is pushing space itself to stretch faster over time. We call that influenced dark energy because we do not know its nature. It might be a constant property of space that never changes. It might be a field that evolves slowly as the universe ages. It might even mean gravity behaves differently on the largest scales. The mystery matters because it shapes the far future. If acceleration continues, galaxies beyond our local group will slip from view, and the observable universe will grow lonelier with time. A single alien signal could change everything, and we keep listening. The night sky looks calm, but many scientists treat it like a channel that might one day carry a message. A true extraterrestrial signal would likely have properties that make it hard to dismiss, such as narrow bandwidth, clear modulation, repetition, and a sky position that stays fixed among the stars. Even then, the first response would be caution. Observers would try to rule out satellites, aircraft, and terrestrial transmitters. They would ask other observatories to confirm the detection, using different instruments and different locations on Earth. Only after careful checks would the world hear about it, and even then the meaning might remain unknown. A beacon could be intentional, like a lighthouse. It could also be accidental leakage from technology. Either way, confirmation would be a turning point in history, because it would answer one question with stunning clarity. We are not alone in being capable of making signals. That one fact would reshape philosophy, science, and identity at once. Until then, the listening continues in quiet rooms filled with screens, where spikes in data are treated like whispers that might matter. Some galaxies look unexpectedly grown for such an early moment in the universe, which raises questions about our own cosmic timeline. When powerful telescopes look far away, they look back in time. Some of the galaxies seen at extreme distances appear surprisingly bright and organized for such an early era. That suggests stars were forming rapidly, and that heavy elements and dust may have built up faster than many models expected. It raises practical questions. Did the earliest stars grow unusually massive? Did gas cool more efficiently than we assumed? Did black holes form early and help shape their host galaxies? Or are we misreading the light because dust and complex star formation can mimic maturity? Each new survey adds more candidates and better spectra, which helps confirm distances and ages. The mystery is productive. It forces theorists to refine how the first structures assembled out of a young and turbulent universe. The universe might be infinite, or it might wrap around. We know we can see only a limited volume because light has had a limited time to reach us. Beyond that horizon, space continues, but its overall shape is still an open question. One possibility is endless extension, with no boundary and no edge. Another is that space is finite yet unbounded, more like the surface of a sphere, where traveling far enough in one direction could, in principle, bring you back. Some models allow more intricate shapes, like a three-dimensional hall of mirrors, where patterns repeat at vast scales. Astronomers test these ideas by searching for repeated structures in the cosmic microwave background and by studying how galaxies are distributed across the sky. So far, the data do not give a final answer. The mystery is humbling. The universe may be far larger than anything we can ever observe. We do not know what happened before the Big Bang. The earliest moments we can describe with confidence come after the universe was already expanding and filled with hot matter and radiation. Before that, our equations become uncertain because they push into energies where gravity and quantum rules collide. Some thinkers treat the question as meaningless because time itself might have begun with the Big Bang, leaving no earlier chapter. Others explore ideas where a previous universe contracted, then bounced into expansion, or where our universe formed as a bubble inside a larger reality. There are also proposals involving quantum creation, where the universe appears as a natural fluctuation of fundamental fields. The challenge is evidence. We need traces that survive from those earliest instants, and nature may have erased them. Still, the question persists, because it is the ultimate origin story. It asks what kind of reality can give rise to time, space, and law. Venus spins backward slowly, and its history is still mysterious. Venus rotates in the opposite direction to most planets, and it does so at a leisurely pace. A day there is longer than its year. That odd behavior suggests something dramatic happened, or that long-term forces quietly reshaped the planet's spin. One possibility is a giant impact early on, the kind that can flip a planet's rotation and leave it wobbling. Another is that thick atmosphere and tides raised by the sun gradually torqued the planet into its current state. Venus also has fierce winds that race around the planet much faster than the ground turns, and that atmospheric superrotation may interact with the solid planet in subtle ways. Understanding the spin matters because it connects to Venus's climate story. Rotation influences circulation, cloud patterns, and how heat moves. Venus is Earth's near twin in size, yet its surface is crushingly hot and its air is heavy with carbon dioxide. The backward spin is one more clue that its path diverged sharply from ours. Mars makes methane sometimes, and its source is still disputed. Methane is intriguing because it does not last very long in a planet's atmosphere. Sunlight and chemical reactions tend to break it apart, so a steady supply is needed to keep it around. On Mars, measurements have hinted at occasional spikes and seasonal patterns, which suggests something is releasing methane now, not only in the distant past. The mystery is what kind of something. Geology can do it. Certain rock-water reactions can generate methane without life, and trapped gas can seep out through fractures. Chemistry in ancient ice could also play a role, releasing methane as conditions change. Biology is the more dramatic possibility, since microbes on Earth can produce methane as a waste product. The problem is that different instruments and different methods have not always agreed, and that makes the signal hard to pin down. The smartest approach is patient, map where methane appears, track how it changes with time, and look for companion gases that could reveal the underlying process. Uranus lies on its side, likely from an ancient collision. This planet rolls around the Sun as if it was tipped over, with its rotation axis pointing almost along its orbit. That means each pole can spend long stretches in sunlight, then long stretches in darkness, like seasons taken to an extreme. One strong idea is that something enormous struck Uranus early on, a protoplanet or a chain of large impacts, and the blow knocked it into its sideways posture. Another idea is that repeated gravitational nudges from forming moons and the early disk slowly twisted it over time. Either way, the tilt is not just a party trick. It affects how the planet's atmosphere circulates, how sunlight warms different layers, and how its magnetic field interacts with space. Uranus also has a magnetic field that is oddly offset and tilted, which adds another layer of strangeness. It is a world that looks like a simple blue orb, but it behaves like a cosmic oddity with a hidden backstory. Neptune's dark storms appear and vanish like bruises on blue skin. Neptune is far from the Sun, yet its winds can roar faster than many storms on Earth. From time to time, giant dark spots form in its atmosphere, and they can be large enough to swallow our planet. These are not holes. They are vortices, weather systems that dredge up deeper layers and change how light is absorbed. What makes them mysterious is their behavior. They can grow, drift, and then fade away, sometimes within a few years, which is a short lifetime for a planet so distant and cold. Bright companion clouds often appear near them, likely methane ice crystals lofted high by rising air at the vortex edges. Telescopes have watched these storms change shape, and newer observations have begun tracking them again after long gaps. Scientists still debate why Neptune is so energetic, and why some storms survive while others dissolve. Each dark spot is like a temporary window into a deep, fast, restless atmosphere. Saturn's hexagon storm persists for years, and it still surprises scientists. At Saturn's North Pole, a jet stream forms a shape that seems almost impossible. A six-sided wave pattern, sharp enough to trace a hexagon, with a stormy eye sitting at its center. It was seen by the Voyager spacecraft, then later studied in exquisite detail by Cassini, and it has remained for decades. The hexagon is not a rigid object. It is a standing wave in the atmosphere, a pattern created by winds flowing at different speeds and by the way rotation organizes motion near the pole. In laboratory experiments, rotating fluids can make polygon shapes like this, which is comforting, but Saturn's version is enormous and enduring. The mystery is in the stability. Why does this pattern hold its edges so cleanly, and why does it resist breaking apart into chaos? Cassini also showed seasonal changes in color and brightness, suggesting chemistry and sunlight influence the structure. It is a reminder that even clouds can form geometry, and that planetary weather can become something like architecture. Jupiter's great red spot is shrinking, and its future is unknown. This storm has raged for centuries, and it is so large that it once could have swallowed multiple Earths. It is an anticyclone, a rotating system with high pressure at its center, and it sips within Jupiter's banded atmosphere like a long-lived whirlpool. Over recent decades, measurements have shown it getting smaller, though it can still tower over our planet in scale. The storm also changes color, sometimes a deeper brick red, sometimes a paler salmon, and the reason likely involves chemistry, sunlight, and how material is our all. Stirred upward from deeper layers, Jupiter's surrounding jet streams feed and shear the spot, and smaller vortices sometimes collide with it, like eddies joining a larger current. Will it fade away or settle into a smaller but stable form? Scientists model the storm's energy budget, its vertical structure, and how it exchanges heat with its surroundings. The mystery feels personal because the Great Red Spot is one of the few cosmic features you can recognize by name, and it is changing before our eyes. Some moons may have hidden oceans warmed by tidal squeezing. A moon does not need sunlight to stay interesting. If it is caught in a gravitational tug-of-war, its interior can flex over and over again, and that flexing creates heat. The process is called tidal heating, and it can keep water liquid beneath an icy shell, even in the cold outer solar system. The key is an orbit that is not perfectly circular. When the moon moves closer to its planet, gravity pulls harder, and when it moves farther away, the pull eases. The constant kneading warms the inside like a bent paperclip that heats at the crease. This idea changes the map of possible habitats. A distant moon can have a long-lived ocean, chemical gradients, and perhaps hydrothermal systems on the seafloor. Scientists look for hints through surface cracking, magnetic signatures and plumes, and by measuring how a moon wobbles as it orbits. Hidden oceans turn small worlds into deep mysteries because they might be both common and concealed. There may be rogue planets drifting starless, invisible in the dark. Not every planet must circle a star forever. In the chaos of young solar systems, close gravitational encounters can fling worlds outward. A planet can be exiled into interstellar space, where it becomes a wanderer between the stars. We cannot usually see such a world directly, because it reflects almost no light. Instead, astronomers search for rare moments when a rogue planet passes in front of a distant star and its gravity briefly magnifies the starlight. That technique is called microlensing, and it has already hinted at lonely planets with masses like Jupiter and perhaps smaller. The idea is haunting. A rogue world could carry an internal heat source from radioactivity or leftover formation warmth, and that heat might keep subsurface water from freezing solid. Darkness does not always mean dead. The laws of physics seem finely balanced, and nobody knows the reason. Many features of our universe depend on numbers that could, in principle, have been different. The strength of forces, the masses of particles, and the way protons and neutrons interact all shape what matter can become. One famous example is carbon. Stars forge it through a delicate sequence of nuclear reactions, and the details depend on just the right energy levels inside atomic nuclei. If those levels shifted, carbon chemistry could be rare, and complex molecules might struggle to appear. Other balances show up in how long stars live and in whether stable atoms can exist. Some people see deep meaning in these coincidences. Others suspect there is a selection effect or a deeper theory waiting to be found. The mystery is not philosophical only. It is a clue that our understanding may still be incomplete. A teaspoon of neutron star material would crush anything on Earth. Neutron stars pack more mass than the Sun into a sphere only tens of kilometers wide. That makes their average density so high that a small amount of their matter would weigh billions of tons in Earth's gravity. It is not only heavy, it is arranged in a way that defies everyday experience. Near the surface, nuclei may form bizarre shapes, sometimes described as nuclear pasta, because the competition between forces can create layers and strands. Deeper down, the boundary between crust and core becomes a transition into matter that is mostly neutrons, with a sprinkling of other particles. If you could somehow place a teaspoon of this material on a table, it would not sit there like a pile of powder. It would fall through, violently compressing whatever was beneath it, until the pressure matched its nature. Of course, it would also instantly expand and change if removed from its native pressure. which is part of why this crushing substance stays safely locked inside. Neutron stars. Antimatter should exist everywhere, yet the cosmos prefers matter. In particle physics, matter and antimatter are twins with opposite charge, and when they meet, they annihilate into energy. The early universe should have made both in nearly equal amounts. If that balance had held, almost everything would have vanished into radiation, leaving a thin fog and little else. Yet here we are, in a universe full of atoms, planets, and chemistry. Something tipped the scales by a tiny amount, leaving a small excess of matter that survived. The leading explanation involves processes that violate certain symmetries, allowing reactions that treat matter and antimatter slightly differently. Experiments study rare particle decays, and they search for subtle asymmetries that could explain the cosmic outcome. The mystery is profound because it connects the smallest lab measurements to the existence of every star and every breath. A minute imbalance became everything. Neutrinos pass through Earth, and most pass through you unnoticed. They are among the most abundant particles in the universe, yet they interact so weakly that they slip through rock, metal, and flesh as if nothing were there. The Sun produces them in vast numbers through nuclear reactions, and distant cosmic events make even more. To catch them, scientists build detectors deep underground, inside Antarctic ice, or under seawater, where shielding blocks other particles. When a neutrino does interact, it can create a brief flash of light in water or ice, like a tiny blue whisper. Each detection is a message from places light cannot easily escape, including the dense cores of stars and the hearts of exploding systems. Neutrinos also carry information about fundamental physics, such as their tiny masses and how they change flavor as they travel. They are elusive, but they are everywhere, turning the universe into a quiet stream of travelers. Some neutrinos arrive with impossible energy, and their sources are debated. A few detections have carried energies so extreme that they force a new level of suspicion. To produce such particles, nature needs accelerators far beyond anything humans can build. One candidate is a blazing galaxy with a supermassive black hole at its center, where magnetic fields and shock waves could fling particles to staggering speeds. Another is the aftermath of violent stellar death, where jets punch through surrounding material and create cascades of high-energy debris. There are also more speculative possibilities, including the decay of heavy relic particles from the early universe. The difficulty is that neutrinos travel almost in straight lines, but the number detected is still small, and pinpointing origins is hard. Each rare event becomes a detective story that combines timing, direction, and other messengers like gamma rays. When one matches up, it feels like the universe briefly lifted a veil. Cosmic rays strike with shocking power, and their origin is unclear. These are not rays in the ordinary sense. They are particles, often protons or heavier nuclei, arriving from space at speeds close to light. When they slam into the atmosphere, they trigger showers of secondary particles that spread across kilometers, and ground arrays can record the cascade. Some arrive with energies that make a tossed baseball seem slow and gentle by comparison, and that raises the question of what launched them. Supernova remnants can accelerate particles through expanding shock fronts, and that likely explains many. The highest energy visitors are harder to place. They may come from active galaxies, from colliding galaxy clusters, or from rare cataclysms we have not fully recognized. Magnetic fields bend their paths, which makes it difficult to trace them back like arrows. Even so, patterns in arrival directions and composition are starting to hint at answers. The mystery is a reminder that space is not only vast, it is energetic and restless. Gamma ray bursts can sterilize planets, yet they are still poorly understood. For a few seconds, a gamma-ray burst can release more energy than the Sun will emit over its entire lifetime, and much of that energy can be funneled into narrowed Methane. Jets. If one of those jets were aimed at a nearby habitable planet, high-energy radiation could damage ozone and drive harsh changes in atmospheric chemistry. Luckily, such bursts are rare in any one galaxy, and the jet must point directly toward the target. Even so, they are powerful enough to shape ideas about how often life can persist in certain regions of the cosmos. We now know there are at least two main kinds. Some are linked to massive stars collapsing, and others to mergers of neutron stars. Yet the detailed physics of the jets, the magnetic fields, and the particle cascades remains an active puzzle. Each burst is a brief lighthouse, announcing extreme events across the universe, then disappearing before we fully grasp it. Magnetars have magnetic fields so strong they warp atoms themselves. These neutron stars are born in violence, and they carry magnetic fields so intense that matter behaves in unfamiliar ways. In a magnetar's grip, electrons are forced into tight spirals, and atoms become stretched and distorted along magnetic lines. The star's crust can also crack under magnetic stress. When it does, the surface can jolt like a starquake and unleash a giant flare. Some of these flares are so bright that if one happened close enough, it could briefly affect Earth's upper atmosphere. Magnetars also produce eerie signals in X-rays and gamma rays, and they can pulse like a heartbeat that refuses to settle. A few fast radio bursts have been linked to magnetar outbursts, which makes them suspects in one of astronomy's newest mysteries. They are small, dense, and utterly extreme, like physics turned up to its loudest setting. Pulsars are cosmic lighthouses, and some spin faster than kitchen blenders. A pulsar is a neutron star that sweeps a beam of radiation through space as it rotates. If that beam crosses Earth, we see a pulse, then another, with astonishing regularity. Some spin only a few times each second. Others, called millisecond pulsars, whirl hundreds of times per second, which makes their surface speeds mind-bending. Their steady timing is so precise that astronomers use them like celestial clocks. By tracking tiny changes in pulse arrival times, scientists can discover companion stars, map the distribution of matter between the stars, and even build galaxy-scale detectors for low-frequency gravitational waves. Pulsars also act as laboratories for dense matter, because their mass and size can be measured through their timing. It is hard to imagine a more dramatic transformation. A star collapses, and what remains becomes a beacon that can keep time across the Milky Way. Some pulsars glitch suddenly, like a star skipping a beat. Most pulses arrive with reassuring steadiness, and then a pulsar can abruptly spin a little faster. The change is small, but it is unmistakable. It is as if the star has been saving up angular momentum and then releasing it in a single step. One leading idea involves the neutron star interior. Beneath the crust, parts of the star may behave like a superfluid, which can store rotation in a different way than normal matter. When that hidden component reconnects with the crust can be tugged forward. Another possibility involves the crust itself shifting as it cools and stresses build. After a glitch, the pulsar often relaxes slowly, like a clock finding its rhythm again. These events are precious because they offer rare clues about the unseen layers inside neutron stars. We cannot drill into them, so we wait for them to stumble and reveal their secrets. Fast-spinning neutron stars may hide exotic matter in their cores. Neutron stars are already strange, but the deepest regions may be stranger still. The pressure in the core can exceed anything we can reproduce on Earth, and that pressure may force matter into new states. Some models suggest neutrons and protons could dissolve into a sea of quarks. Others allow hyperons, heavier relatives of ordinary particles, to appear. There are even proposals for more exotic phases where matter becomes a kind of dense soup with unusual symmetries. Rotation matters because it changes the star's shape and internal balance. A rapid spin can support a slightly larger mass before collapse, and it can affect how heat and magnetic fields move through the interior. By measuring masses, radii, and how neutron stars deform in mergers, astronomers try to narrow down what is possible inside. Every observation is a constraint on the recipe of ultra-dense matter, and the core remains one of the most secret places in the universe. Some radio bursts last milliseconds and outshine whole galaxies. Fast radio bursts appear as sharp pops in radio telescopes, and many last only a few thousandths of a second. Even so, their brightness implies an enormous release of energy, packed into a brief blink. Some bursts repeat from the same region of sky, which suggests a long-lived engine. Others have been seen only once, which hints at a catastrophic event. The signals arrive smeared across frequencies, which reveals how much charged material they traveled through on their journey. That makes them not only a mystery, but also a tool. By tracking where they come from, astronomers have linked some to distant galaxies and to extreme environments. Magnetars are strong suspects for at least part of the population, but the full story is still unfolding. We might be missing most of the universe's normal matter. Even after accounting for stars, planets, and glowing gas, ordinary matter seems to come up short when compared with what the early universe predicts. This is not dark matter. It is the familiar kind made of protons and neutrons. The leading idea is that the missing material is spread thinly through space as warm to hot gas, stretched along the filaments between galaxies. It would be hard to see because it is faint and diffuse. Astronomers hunt for it by looking for subtle absorption fingerprints in ultraviolet and X-ray light from distant sources, and by mapping how hot gas scatters the cosmic microwave background. In recent years, evidence has been building that much of it really is out there, hiding in the cosmic web. The mystery is a reminder that even the ordinary can be hard to find. Black holes hide their interiors forever, and physics still argues about it. A black hole is not just a heavy object. It is a region where escape becomes impossible once you cross a boundary called the event horizon. Light can orbit near it, but inside the horizon, every path leads deeper inward. That makes the interior hard to describe with confidence. Our best theory of gravity predicts a singularity where density and curvature blow up, which is usually a sign that the theory has reached its limits. Meanwhile, telescopes can study what happens outside. Gas heats to extreme temperatures as it spirals in, and jets can punch outward for light years. We have even imaged a dark shadow surrounded by glowing plasma. The inside remains hidden, like a sealed room whose door opens only one way. We can hear spacetime ring after black holes collide. When two black holes spiral together, they do not crash like rocks. They stir the fabric of spacetime and send out gravitational waves. On Earth, detectors like LIGO and Virgo measure those waves as tiny changes in distance, smaller than a proton, across kilometer-long arms. The signal rises in pitch and volume as the orbit tightens. Then comes a final moment of merger, followed by a fading tone called the ringdown. That ringdown is the newborn black hole settling into shape, like a struck bell losing its vibrations. By matching the sound to theory, scientists can estimate masses and spins, and they can test whether gravity behaves as Einstein predicted under extreme conditions. It is astronomy done with listening. The universe has a cold spot, and its cause is uncertain. In the cosmic microwave background, the faint afterglow of the early universe, there is a region that looks a little cooler than its surroundings. The difference is small, but it is large on the sky, which makes it hard to ignore. One possibility is simple chance. Random fluctuations can produce unusual patches now and then. Another idea is that we are looking through an enormous underdense region, a cosmic void that lets light lose a bit of energy as it travels. Some scientists have even explored more exotic explanations that involve unusual structures in the early universe. The cold spot sits at the border between anomaly and discovery. It reminds us that the universe still keeps secrets, even in its oldest light. Dark matter outweighs stars, yet no one has ever seen it. When astronomers measure how fast galaxies spin, the outer stars move as if extra mass is holding them in orbit. The visible matter is not enough. The same hidden pull shows up when galaxies bend background light into arcs, and when clusters crash through each other and their gravity ends up separated from their gas. It is as if most mass is present only through its gravity. For decades, laboratories have tried to catch dark matter as it drifts through Earth. So far, detectors have heard mostly silence. That silence is part of the mystery. Whatever it is, it does not shine. It rarely bumps into normal atoms, and it shapes the architecture of the cosmos. Stellar nurseries hide behind dust, and infrared eyes reveal them. The places where stars are born are often wrapped in thick clouds of cold gas and dust. In visible light, those clouds can look like dark holes punched into the Milky Way. Inside, gravity gathers material into dense knots, and those knots heat as they collapse. The earliest phases are hidden from ordinary telescopes, but infrared light can slip through the dust far more easily. With infrared cameras, a once black patch becomes crowded with newborn stars, glowing disks, and jets that carve narrow cavities into the surrounding cloud. Radio telescopes add another layer, tracing molecules that mark temperature, density, and motion. In these regions, you can watch a story unfold. A cloud fragments, multiple stars form at once, and their radiation begins to blow the remaining gas outward. The same dust that blocks our view also becomes part of the next generation because it helps build planets. Star formation is not a clean event. It is a crowded, messy, and astonishingly creative process. Brown dwarfs are failed stars, and their boundary is still fuzzy. Brown dwarfs form like stars by collapse of a gas cloud, but they never become hot enough in their cores to sustain normal hydrogen fusion for long. They sit in the middle ground between planets and stars, and that middle is not a sharp line. Some brown dwarfs can briefly fuse deuterium, a heavier form of hydrogen, early in their lives. That provides a kind of faint ignition that quickly fades as the fuel runs out. Because they are cool and dim, many were missed until infrared surveys began to uncover them. Their atmospheres can host clouds made of exotic minerals, and their weather may include storms unlike anything on Earth. Some even have auroras, hinting at strong magnetic activity. The mystery is partly a naming problem. At what point does a massive planet become a brown dwarf? And when does a brown dwarf deserve to be called a star? Nature does not always respect our categories. Some stars dim oddly, and the simplest explanation is not settled. Most stars vary in brightness for familiar reasons. Star spots rotate in and out of view, planets transit like tiny eclipses, and dusty disks can cause smooth fading. Yet a few stars show dips that are irregular, deep, and difficult to predict. In some cases, the dimming events do not repeat on neat schedules, which makes them hard to tie to a single orbiting planet. Astronomers respond like detectives. They check whether the star itself is unstable, whether surrounding dust grains could clump and scatter light in unusual ways, and whether swarms of comets could create shifting veils as they pass. Spectra can reveal whether the star's light is being filtered, which can point toward dust rather than something solid. Public imagination sometimes leaps to extravagant ideas, and scientists take those ideas seriously enough to test them, then follow the evidence where it leads. The excitement is real. A star that refuses to behave is an invitation to learn something new about stellar systems and about our own assumptions. The cosmic microwave background is baby light, still filling all space. This glow began when the universe cooled enough for electrons to settle onto nuclei, letting light finally travel freely instead of bouncing endlessly off Team Bell. Charged particles. That moment happened long before stars existed, so the light carries a record of a cosmos that was still simple, hot, and smooth. Today, it arrives from every direction as microwaves, chilled to just a few degrees above absolute zero by billions of years of expansion. It is so uniform that early observers were stunned, and yet it is not perfectly even. Spacecraft have mapped tiny temperature differences across the sky, and those faint variations act like a fossil photograph. When you look at this background, you are not seeing a place. You are seeing a time stamped across the whole sky. Tiny ripples in that ancient glow became today's galaxies. Those slight warm and cool patches were not weather. They were minute differences in density, where gravity had a little more to grab. Over immense time, the denser regions pulled in more matter, growing from subtle wrinkles into vast structures. The less dense regions became cosmic voids, the quiet valleys between crowded filaments. The beauty is that these ripples can be measured precisely, and their pattern acts like a barcode for the universe's ingredients. The sizes of the patches tell scientists how fast sound waves once moved through the early plasma, and they help reveal how much ordinary matter was available to clump. Later, when the first stars finally ignited, they did so inside these seeded wells. In a real sense, every spiral almond star cluster began as a near-invisible tremble in ancient light. Inflation may have happened faster than light, in the first heartbeat. This idea was invented to explain why the universe looks so similar in opposite directions, and why space appears so close to flat on the largest scales. The proposal is that a brief burst of rapid expansion stretched a tiny, uniform region into something enormous. That expansion would not be objects moving through space faster than light. It would be space itself growing, which relativity allows. If inflation happened, it would have smoothed away sharp curvature and diluted odd relics that would otherwise crowd the universe. It also offers a curious bonus. Quantum fluctuations, which are normally microscopic, could have been stretched to astronomical sizes, becoming the seeds for later structure. Scientists look for its fingerprints in the statistical pattern of the cosmic microwave background and in possible signals from primordial gravitational waves. White dwarfs can explode, and we still refine why some do. A white dwarf is the compact ember left after a sun-like star finishes its life. It is supported by a quantum rule that resists further collapse, so it can persist for billions of years. Yet in the right circumstances, it can become unstable. If a white dwarf pulls gas from a nearby companion star, that new material can pile up on its surface. Sometimes the surface layer ignites in a runaway flash, producing a nova that can brighten dramatically, then fade. In other cases, the buildup can push the white dwarf toward a critical mass, where the interior can ignite in a catastrophic thermonuclear explosion. That event can outshine an entire galaxy for a short time. Scientists still work to pin down the exact pathways, because the details depend on composition, mixing, and how the companion feeds the dwarf. It is a quiet remnant that can suddenly become one of the brightest things in the universe, and that contrast is part of the mystery. Type ER supernova measure the cosmos, yet their details are tricky. These explosions are prized because they can be used to estimate enormous distances. They tend to reach similar peak brightness, and astronomers can adjust for differences by tracking how quickly the light fades. That made them a cornerstone for discovering cosmic acceleration. The trouble is that nature rarely gives a perfect standard. Some type IR events may come from a white dwarf steadily gaining mass from a companion. Others may come from two white dwarfs spiraling together and merging. Those different origins can subtly change the amount of nickel made, which affects how bright the explosion becomes and how the light curve behaves. Dust in the host galaxy can also dim and redden the light in ways that are hard to untangle. Researchers tackle this by studying nearby examples in detail and by building huge samples that reveal patterns. The method remains powerful, but the story behind each explosion is still being sharpened, and that matters when you are measuring the fate of the universe. The WOW signal was real, and it never returned. On an August night in 1977, a radio telescope called Big Ear was scanning the sky when it caught a narrowband signal that rose, peaked, and faded over about 72 seconds. A researcher later circled the printout and wrote, "Wow," and the name stuck. The frequency sat close to the hydrogen line, a natural place to listen because hydrogen is everywhere in the cosmos. The strange part is what happened next. Follow-up observations listened again and again, and nothing matched it. No repeating beacon. No obvious human source that could be confirmed. That leaves a mystery shaped like a single footprint. It could have been an unusual reflection, a rare astrophysical event, or something engineered that swept past once and moved on. It remains a reminder that one clean anomaly can haunt science for decades. The Fermi paradox asks why the galaxy feels so quiet. The Milky Way is ancient, and it contains hundreds of billions of stars. Many are far older than the Sun, which means a technological civilization could have had immense time to spread, to build, to leave signs. Yet when we look out, we see no obvious traffic, no cities across the stars, no unmistakable signals. That tension is the heart of the paradox. It is not proof that we are alone. It is a prompt to think carefully about what we assume. Maybe life is rare, or intelligence is fragile. Maybe advanced societies do not broadcast. Maybe they live in ways that are hard to notice, using low-power communication or staying close to home. It is also possible we are early, or simply listening in the wrong way. The silence is a data point, and it turns a big question into a careful search strategy. We do not know how often life begins, even with billions of worlds. We can count planets now, and the numbers are staggering. What we cannot count is the step from chemistry to biology. Life requires more than water and warmth. It needs stable environments, useful energy sources, and complex molecules that can copy themselves with enough fidelity to evolve. On Earth, life appeared early, but we do not know whether that means it is easy or whether we got lucky once. We also do not know the true range of life's possible chemistries. Could it begin in alkaline vents beneath an ocean, inside icy crusts warmed by tides, or in transient pools that dry and refill? Laboratory experiments can build amino acids and other ingredients, but ingredients are not a living system. Until we find a second example, every estimate is a wide band of possibility, and that uncertainty keeps the question thrilling. The Drake equation is famous, yet its numbers remain guesses. This equation is not a prediction machine. It is a way to organize wonder into parts that can be studied. It asks how many civilizations might be detectable right now, and it breaks that into questions we can attack one by one. How many stars form? How many have planets? How many planets might be suitable for life? How often life appears? How often intelligence and technology arise? How long a society stays detectable? Some of those pieces are becoming less mysterious. Exoplanet surveys have shown that planets are common, and that alone changed the conversation. Other pieces remain foggy, especially the biological and social ones. The power of the equation is that it turns a single, overwhelming question into a set of smaller ones, each with its own research program. Even when the numbers are uncertain, the structure keeps the search honest, and it reveals what we truly do not know. Some planets may be ocean worlds, with no land anywhere. Imagine a planet where every continent is drowned, not by a shallow sea, but by an ocean hundreds of kilometers deep. Such worlds may form when a planet gathers abundant water, or when ice-rich bodies merge during early chaos. At first, that sounds like paradise, but the mystery lies in the details. With so much water, pressure at the bottom becomes immense, and that can create exotic high-pressure ice that behaves more like rock than ice. If that layer forms, it could separate the ocean from the rocky mantle below, which might limit the chemistry that feeds life on Earth. On the other hand, ocean worlds could still have internal heat, and their seas could circulate for eons. They might also have thick atmospheres that trap warmth. We have hints of water-rich planets from mass and size measurements, but proving a global ocean is difficult. Each candidate is an invitation to rethink what habitable really means. Europa likely has a sea, and we still have not tasted it. Europa looks like a cracked eggshell, bright ice scored by long lines and jumbled regions where the surface seems to have broken and refrozen. That terrain hints at a warm layer below, and multiple lines of evidence suggest a global ocean under the crust. Europa orbits Jupiter in a way that flexes it like a stress ball. That tidal squeezing can generate heat inside, keeping water liquid far from the sun. Magnetic measurements also suggest a conductive layer, consistent with salty water. If there is an ocean, it may be in contact with rock, and that contact matters. Rock and water together can drive chemistry, and chemistry can build complexity. The mystery is access. The ice shell might be thin in places and thick in others, and we do not yet know where the best windows are. Future missions aim to map the shell, probe the chemistry, and search for signs of active exchange between ocean and surface. Enceladus sprays ocean water into space, carrying complex chemistry. This small moon of Saturn has a south pole that behaves like a geyser field. Long fractures in the ice vent jets of water vapor and ice grains, and those plumes arc outward into space. A spacecraft can fly through them and sample the material directly, which is almost unbelievable as a scientific gift. The plume particles contain salts, which points to liquid water interacting with rock. They also contain organic molecules, the building blocks of more complicated chemistry. Some measurements suggest that tiny grains of silica may form when hot water meets rock at the seafloor, hinting at hydrothermal activity. That combination, water, rock, heat, and organics, is exactly the mix that makes astrobiologists lean forward. The mystery is what the ocean is like, and whether it has stable energy gradients that could support life. Enceladus turns a distant moon into a place you can, in a sense, taste. Titan has rivers and lakes, but they are made of methane. Titan is wrapped in a thick haze, and for a long time it hid its surface completely. Then radar mapping revealed something astonishing. Channels carved like riverbeds, shorelines with bays and inlets, and dark, smooth lakes gathered near the poles. The temperatures are so low that water ice behaves like rock, while methane and ethane can flow as liquids. Titan, in other words, has a weather system that echoes Earth's, but with different chemistry. Methane evaporates, forms clouds, and falls as rain. It pools, it erodes, it reshapes landscapes. A probe once drifted down through the orange sky and landed on a surface scattered with rounded pebbles, as if shaped by flowing liquid. Titan's mystery is not only its strange hydrology, it is the chemistry happening in that thick atmosphere, where sunlight and particles from Saturn's magnetosphere can build complex organics. Titan may be a living laboratory for how prebiotic chemistry behaves on a world unlike our own. Io is the most volcanic world, driven by relentless gravity games. Io orbits Jupiter in a tight dance, and other moons tug on it just enough to keep its orbit slightly stretched. That tiny stretch is everything. It means Io is constantly flexed by Jupiter's gravity, and the repeated squeezing heats its interior until rock melts. The result is a world of volcanoes so active that its surface can change within months. Plumes can rise hundreds of kilometers high, and fresh lava can paint the landscape in new colors, from sulfur yellows to dark basalt. Io is effectively an exposed engine room, showing what tidal heating can do when it is pushed to an extreme. The Moon's volcanoes also feed a torus of material around Jupiter, adding charged particles to the giant planet's magnetic environment. Watching Io is like watching geology on fast forward. It is a place where the sky can glow with volcanic gases, and where a moon, not a planet, holds the title for volcanic power. Mercury has water ice at the poles, despite blazing days. Mercury sits close to the Sun, so its daytime surface can become incredibly hot. Yet near its poles are craters that never see sunlight. Because Mercury's axis is only slightly tilted, the floors of some polar craters remain in permanent shadow, and those shadows can be cold enough to trap ice for billions of years. Radar observations first hinted at bright deposits in these regions, and later spacecraft measurements supported the idea that water ice is present, often coal, buried under a thin blanket of darker material. That cover may be dust and organics delivered by impacts, acting like insulation that slows sublimation. The mystery is where the ice came from and how it survived. Comets and water-rich asteroids are strong suspects, and solar-wind interactions may also play roles in surface chemistry. Mercury's polar ice is a paradox that forces you to remember that temperature in space is about sunlight, not distance alone. Even near the Sun, darkness can preserve a deep, cold archive. The Moon's far side looks different, and we debate why. The near side, the face we see from Earth, is marked by large, dark plains of ancient lava. The far side has far fewer of these maria, and it is more heavily cratered, with a thicker crust on average. This split personality has prompted many ideas. One possibility is that the early Moon had an uneven distribution of heat-producing elements, which could have made one side melt more easily. Another is that Earth's warmth in the Moon's early days influenced how the near side cooled, changing crust formation. Giant impacts also mattered, since the near side includes huge basins that were later flooded by lava, and the far side has a different impact history. Gravity mapping has revealed mass concentrations beneath some basins, and those structures hint at deep internal differences that shaped later volcanism. The far side is not merely hidden. It is a different chapter of lunar history, and understanding it helps explain how rocky worlds cool, crack, and evolve. Some asteroids are piles of rubble, barely held together. Not every asteroid is a single solid boulder. Many are loose collections of rocks and dust, clumped together by weak gravity after past collisions shattered larger bodies. These rubble piles can spin, wobble, and shift internally. Some are so fragile that a close pass by a planet can reshape them, pulling material into a new configuration. Space missions have shown surfaces covered with boulders, fine regolith, and unexpected slopes that would behave differently under Earth gravity. This matters for more than curiosity. If we ever need to deflect an asteroid, a rubble pile might respond in surprising ways. Push too hard and you might scatter it, or you might only rearrange the pieces. Rubble piles also preserve history. Their fragments are samples of older bodies, mixed together like a cosmic rockslide. When a spacecraft touches down and stirs up dust, it is interacting with an object that is more like a floating gravel heap than a mountain. The mystery is how these bodies stay together and how they change over time under sunlight, rotation, and repeated impacts. Comets may have delivered water, but the story is complicated. Comets are icy visitors from the outer solar system, and they can carry water, carbon compounds, and other ingredients that matter for habitability. Early Earth was battered by impacts, so it is tempting to picture comets as cosmic couriers, dropping oceans and chemistry onto a young planet. The complication is that there are multiple sources of water, and not all comet water matches Earth's water perfectly when scientists compare isotopes. Some comets have ratios that are too different, which suggests they cannot be the only source. Water-rich asteroids from the outer part of the asteroid belt are also contenders, and their isotopic signatures can be closer. The likely answer is a blend of deliveries from different populations over time, plus water that was already present in Earth's building blocks. Comets still matter because they bring a cold, preserved record of the early solar system. When they warm near the sun and grow tails, they are not only beautiful, they are ancient messengers, shedding clues about how worlds got their ingredients. The Oort cloud is predicted, yet no one has observed it directly. Far beyond the planet, there may be a vast halo of icy bodies surrounding the sun, so distant that even our best telescopes cannot pick out individual B members. Its existence is inferred from the paths of long-period comets that arrive from every direction, as if launched from a spherical reservoir. The idea is that early in solar system history, the giant planets scattered countless icy leftovers outward. Passing stars and the slow pull of the Milky Way then nudged those objects into a distant swarm. Occasionally, one is disturbed again and falls inward, becoming a comet with a first and often final visit to the inner system. If the cloud is real, it is a fossil archive of solar system formation, preserved in deep cold and darkness. The mystery is simple and delicious. We believe it is there, yet we have never seen it. Interstellar objects pass through our system, and we barely notice. For most of history, we assumed every small body near the sun belonged to our own family. Then we caught visitors that move too fast and on trajectories that do not fit a bound orbit. That means they are not returning. They are passing through, like messages that never intended to stop. The strange part is not that they exist. Space between stars is enormous, and other systems must shed debris during their formation. The strange part is how easily they can slip by unseen. They are small, dark, and fast, and our surveys cover only slices of the sky at any moment. Even when we detect one, we usually do so late, after it has already rounded the sun and is leaving. Each interstellar object is a sample of another star's building materials, carried to us without a spacecraft. We are learning to watch better, because every new visitor could rewrite our assumptions about how planetary systems grow. One interstellar visitor looked like a cigar, and arguments still echo. When that first confirmed interstellar object was discovered, it immediately broke expectations. Its brightness changed dramatically as it tumbled, which suggested an unusually elongated shape, or perhaps a flattened one seen at changing angles. It also seemed to accelerate slightly as it left the Sun, more than gravity alone would predict. That set off a storm of hypotheses. Some researchers suggested outgassing, like a comet producing a small thrust, but without the obvious dusty tail we associate with comets. Others proposed exotic compositions, such as hydrogen or nitrogen ice, that could sublimate invisibly. A few voices floated the possibility of artificial origin, which drew headlines and heated debate. What matters most is that the object exposed how little we know about debris from other stars. With a sample size of 1, every explanation feels precarious. The arguments will calm only when more interstellar visitors are found and compared, and that hunt has already begun. Some meteors come from far away, and their paths tell stories. Most meteors are crumbs from comets or asteroids that have long orbited the Sun. Yet a tiny fraction may arrive with speeds and directions that hint at a more distant origin. When a meteor streaks through the atmosphere, networks of cameras can triangulate its trajectory, reconstruct its pre-entry orbit, and estimate its incoming speed. That is where the detective work lives. If the computed orbit is not bound to the Sun, the meteor could be an interstellar grain, a speck that wandered for ages before meeting Earth. The challenge is that measurements must be extremely precise. Atmospheric drag, fragmentation, and timing errors can blur the reconstruction. Even so, the idea is thrilling. A grain smaller than a pebble can carry the chemical fingerprint of another stellar nursery. If confirmed, such meteors would be the most accessible extraterrestrial material imaginable, arriving for free and burning across our sky like a brief signature. Every well-tracked fireball is a chance to learn where it truly came from. Earth's atmosphere is a shield, yet space weather can punch through. High above the clouds, Earth is constantly struck by particles and radiation from the Sun. Most of it is deflected by our magnetic field or absorbed by the upper atmosphere, which is why life can flourish at the surface. Still, when the Sun becomes stormy, that shield can be stressed. Energetic particles can cascade along magnetic lines toward the poles, lighting auroras and altering the chemistry of the upper air. Radio signals can bend strangely or fade, especially at high latitudes. In extreme cases, induced electric currents can flow through long conductors on the ground, including power lines and pipelines. The atmosphere protects us, but it is also a dynamic interface, not a static wall. Understanding that interface is part of understanding habitability. A planet can have air and still be vulnerable, depending on its magnetic field, its star's temperament, and how often it is hit by strong eruptions. Space weather reminds us that the Sun is not just a light bulb, it is an active neighbor. Solar storms can cripple technology, and we cannot predict them perfectly. A major solar eruption can begin with a sudden release of magnetic energy near the Sun's surface. That can fling a cloud of charged plasma into space, and if it is aimed toward Earth, it can rattle our magnetic field like a struck drum. Satellites may experience increased drag as the upper atmosphere swells, shifting their orbits. Electronics can be damaged by energetic particles, and sensors can be overwhelmed by noise. Aviation routes near the poles can be affected by radio disruptions and elevated radiation levels. On the ground, power grids are at risk when geomagnetic disturbances drive currents through transmission networks. Forecasting has improved, but it still carries uncertainty because we cannot yet measure the Sun's magnetic structure with perfect detail, and because the interplanetary Space between Sun and Earth is turbulent. We often know a storm is coming, but not exactly how strong it will be when it arrives. This is one of the rare cosmic mysteries that touches daily life, because our civilization now depends on delicate systems exposed to a restless star. The Sun's outer atmosphere is hotter than its surface, mysteriously. The Sun's visible surface, the photosphere, is thousands of degrees hot. That already sounds intense. Yet above it lies the corona, a faint extended atmosphere that can reach millions of degrees. Heat usually fades as you move away from a source, so this temperature rise is a long-standing puzzle. The leading suspects are magnetic. The Sun's surface is threaded with fields that twist, tangle and snap as the plasma churns. Small-scale eruptions and rapid waves may dump energy upward, heating the corona in bursts too fine to see as individual events from far away. Space missions that skim close to the Sun have begun measuring the corona's environment directly, sampling particles and fields where the heating is thought to occur. Still, a complete explanation remains slippery, because multiple processes may contribute at once, and the corona changes from moment to moment. Solving this mystery is not just academic. The corona is the birthplace of the solar wind, and understanding its heat helps explain how the Sun influences the entire solar system. The solar wind shapes invisible bubbles around planets and comets. The Sun constantly exhales a stream of charged particles that flows outward in all directions. This solar wind is not a breeze you could feel, but it has force, and it carries magnetic fields with it. When that flow meets a planet with a strong magnetic field, it creates a protective cavity called a magnetosphere, a kind of invisible bow wave that deflects incoming particles. Earth has one, Jupiter has an enormous one, and even Mercury has a small but active version. Planets without a strong global field can still form a different kind of shield, where the solar wind interacts directly with the upper atmosphere and ionizes it. Comets respond dramatically. As they warm, they release gas that becomes electrically charged, and the solar wind then sculpts a plasma tail that points away from the Sun, sometimes whipping and snapping as conditions change. These bubbles and tails are shaped by a hidden conversation between particle streams and magnetic forces. It is space weather as sculpture, and it turns emptiness into structure. Space is not empty. It has fields, dust, and whispering plasma. Between planets and stars, there is far less matter than in any vacuum chamber on Earth. But there is not nothing. There are magnetic fields stretched and twisted across vast distances. There are thin gases, often ionized, that behave as plasma and respond to fields in ways ordinary air does not. There is dust, grains smaller than smoke particles, drifting through sunlight and slowly spiraling under subtle forces. There are also energetic particles, relics of old explosions and active stars, threading through the darkness. This thin material matters because it carries messages. It can scatter light, absorb certain wavelengths, and seed new clouds when conditions are right. It can also interfere with spacecraft, charging surfaces and creating tiny hazards over long missions. The more we study interplanetary and interstellar space, the more it looks like a dynamic environment, full of currents and boundaries, not a blank stage. The mystery is that so much structure can arise from so little substance. Magnetic reconnection snaps like a cosmic rubber band, releasing fierce energy. Magnetic fields store energy when they are forced into stressed shapes, and in a plasma they can be pushed, folded and squeezed by flowing charged particles. Sometimes two regions of field with different directions are driven together, and the configuration suddenly rearranges. Field lines break and reconnect into a new pattern, and the stored energy is released into heat, light, and fast particles. This process powers solar flares and helps launch eruptions that race through the solar system. It also occurs in Earth's magnetosphere, where it can inject particles into near-Earth space and intensify auroras. Reconnection is one of the ways the universe converts orderly field energy into violent motion. The challenge is that it happens on scales both huge and tiny at once, with details controlled by microphysics that are hard to capture in a single model. When we observe a flare's sudden brightening, we are watching reconnection at work, a rapid rewrite of magnetic geometry with real consequences. Gravity waves from the early universe might still be detectable. These are not ocean waves. They are ripples in spacetime itself, and some may have been made before the first atoms existed. In the earliest instance, the universe was a hot, dense arena where quantum fluctuations could have been stretched to cosmic size. If that happened, it may have stirred spacetime and left a faint background of gravitational waves that still fills the cosmos today. Unlike light, these waves would pass through the early universe's fog without being scattered, which means they could carry information from times we cannot otherwise see. Scientists search for their fingerprints in subtle patterns of polarization in the cosmic microwave background, and they also hope future detectors in space will listen at frequencies no ground instrument can reach. Finding this background would be like hearing an echo from the universe's first breath, and it would turn speculation into a measured story. We do not know whether black holes destroy information. When something falls into a black hole, the outside universe can no longer see the details. Only the mass, spin, and electric charge remain visible. That seems to erase the information about what the object was and how it was arranged. Quantum physics dislikes that idea because it treats information as something that cannot simply vanish. This tension has become one of the most famous arguments in modern physics. If black holes truly erase information, then quantum rules may need rewriting. If they do not, then the information must be hidden in some subtle way, perhaps encoded on the horizon or released extremely slowly as the black hole changes. The debate is not only philosophical, it shapes how we think about space, time, and the meaning of a boundary you cannot cross and report back from. Black holes force us to ask whether the universe keeps perfect records, even in its darkest places. Hawking radiation is predicted, yet it has never been measured directly. The prediction is almost poetic. Quantum physics suggests that empty space is not truly empty, because particle pairs can flicker into existence briefly. Near a black hole, one member of a pair could fall inward while the other escapes. To an outside observer, it would look as if the black hole is emitting radiation, slowly losing energy in the process. The effect is expected to be incredibly faint for astrophysical black holes, far weaker than the glow of surrounding gas and far colder than the microwave background that fills the universe. That makes direct detection extremely difficult. Still, the idea is central because it links gravity, quantum theory, and thermodynamics in a single statement. Scientists explore analog experiments where horizons are mimicked in fluids or light guides, hoping to learn how such emission behaves. Measuring the real thing would be a landmark because it would confirm that black holes are not perfectly black and that quantum effects can leak out of gravity's strongest, quote, traps. Black holes might evaporate, but the timescales are mind-bending. If Hawking radiation is real, then black holes do not last forever. They lose energy in tiny amounts, and over unimaginable time they could shrink. The strange twist is that the smaller a black hole becomes, the faster it is expected to radiate, which means evaporation would start slow and end in a rapid sheen. Finale. For stellar mass black holes, the lifetime would be far longer than the current age of the universe. Even for smaller black holes, if any exist, the lifetimes can still be enormous. This stretches intuition. We are used to endings that unfold within years, lifetimes, or at most geological eras. Black hole evaporation lives on a timescale that makes galaxies feel temporary. It also raises sharper questions. If a black hole disappears completely, what happens to whatever fell in? Does the information return, or is it lost with the last burst of radiation? The idea turns black holes into clocks, but clocks set to cosmic patience. Some black holes grow too fast, too early, for easy explanations. When we look deep into space, we see quasars that already hosted enormous black holes when the universe was very young. That is a surprise, because growth takes time. A black hole can feed on gas, but feeding is limited by how radiation pushes back on incoming matter. It can also merge with other black holes, but mergers require galaxies to find each other and settle. So, how did some become so massive, so quickly? One possibility is that the first seeds were not small. Perhaps some regions collapsed directly into large black holes before normal stars formed. Another possibility is that feeding happened in bursts, with flows dense enough to overcome typical limits, at least for short periods. There is also the messy role of early galaxies, where gas was abundant and chaotic. Each new observation tightens the puzzle because it pins down masses and distances more precisely. These early giants are not just curiosities. They are signposts that our story of cosmic beginnings may need a faster chapter. A galaxy's central black hole can shape star formation far away. It is tempting to picture a black hole as a cosmic vacuum cleaner, but its real power is in how it feeds. When gas falls toward the center, it heats, glows, and can launch energy outward through winds, radiation, and jets. That outflow can push on gas across the galaxy and even beyond it, changing the supply of raw material for new stars. In some cases, the energy may clear gas away, shutting down star formation and leaving an aging galaxy behind. In other cases, shock waves can compress clouds and spark bursts of star birth, like a match striking dry tinder. This is called feedback, and it is one of the reasons galaxies have the sizes and shapes we see. The mystery is in the details. Feedback can be gentle or violent, steady or episodic, and it depends on how gas flows through a complex galactic ecosystem. A black hole can be tiny compared to its galaxy, yet it can still influence the fate of billions of stars. Quasars shine across the cosmos, powered by feeding black holes. A quasar can outshine its entire host galaxy, and it does so from a region smaller than our solar system. The engine is a supermassive black hole surrounded by an accretion disk, where gas spirals inward and heats to extreme temperatures. As the gas loses energy and angular momentum, it releases light across the spectrum, from radio to X-rays. Some quasars also drive jets that shoot outward at near light speed, and those jets can inflate giant lobes far outside the galaxy. Quasars are valuable because they act like backlights. Their bright beams reveal the otherwise invisible gas between galaxies through absorption lines, letting astronomers map matter along the line of sight. They also mark eras when galaxies were growing rapidly. The mystery is how these feeding episodes turn on and off, and how the flow stays organized rather than being torn apart by turbulence. A quasar is a lighthouse powered by gravity, and it lets us see the universe at distances that would otherwise be dim and silent. Blazars aim jets at us, and their flickering can be violent. A blazar is a special kind of active galaxy, where one of its jets happens to point almost directly toward Earth. That alignment changes everything. Relativistic effects boost the jet's brightness, shorten the apparent timescales and make its variability look dramatic. A blazar can flare suddenly across multiple wavelengths, sometimes within hours, as if a cosmic spotlight is being shaken. The jet itself is a strange structure, filled with charged particles and threaded by magnetic fields. Shocks can travel down the flow, and magnetic tangles can rearrange, releasing energy in bursts. Some blazars have also been linked to high-energy neutrino detections, which hints that their jets may accelerate particles to extreme energies. The flickering is not random noise. It is a code that describes how matter behaves near a supermassive black hole and how energy is transported across light years. Watching a blazar is like watching the universe in a state of bright, restless focus. Jets from black holes can stretch for millions of light years. It is hard to accept that a single central engine can influence space on such grand scales, but some jets do. They emerge from the vicinity of a black hole, stay narrow for astonishing distances, and then inflate lobes where they dump energy into surrounding space. These jets are not made of solid material. They are streams of plasma and magnetic fields, and they can carry enormous power. Along the way, they can punch through the gas between galaxies, heating it and reshaping how it cools. That matters because cooling gas is what can later fall into galaxies and form new stars. Jets can also create bright hotspots where they slam into their environment, producing radio emission that can be mapped across immense volumes. The mystery is how jets remain stable. Over millions of light years, the flow should be challenged by turbulence and instabilities, yet many jets keep their structure like arrows that refuse to scatter. They are among the largest coherent objects in the universe, drawn not with ink, but with magnetism and motion. The event horizon is a boundary, and it tests reality itself. The event horizon is not a physical surface you could touch. It is a mathematical line in spacetime, defined by escape. Outside it, light can still climb away. Inside it, every possible path leads inward. That makes the horizon a one-way border for information, at least from the perspective of the outside universe. It is also where many deep ideas collide. Gravity is extreme there, but it is not necessarily the strongest part, because the horizon can be crossed without special drama for a falling observer in many years. Scenarios. The drama is for us watching from afar, since signals appear to slow and fade. The horizon forces questions about what is real. Is it a mere coordinate effect, or does it carry physical properties like temperature and entropy? The image of a black hole shadow gives us a view of the region around the horizon, but the true boundary remains invisible. It is a line defined by causality itself, and that is why it feels like a test of the universe's rules. Wormholes are allowed by equations, but no evidence has appeared. General relativity permits shortcuts through spacetime, tunnels that could connect distant regions like two doors opening onto the same hallway. On paper, they are called wormholes, and they appear in certain mathematical solutions. The trouble is keeping one open. Gravity wants to pinch the throat closed, and most models require exotic energy that behaves unlike normal matter. Even if such material exists, a wormhole could be unstable, collapsing the moment anything tries to pass through. Astronomers still look for indirect signs, like unusual gravitational lensing that does not match ordinary black holes, or strange timing effects in bar, light from distant sources. So far, nothing has passed the tests. Wormholes sit in that fascinating space between imagination and physics. They are not fantasy, because the math allows them. They remain unconfirmed, because nature has not shown one. Time travel solutions exist on paper, yet nature may forbid them. Relativity already gives a kind of time travel, because clocks tick at different rates when they move fast or sit deep in gravity. That is real, and it has been measured. The more dramatic idea is traveling into your own past. Certain space-time geometries, like rapidly rotating systems or carefully arranged cosmic strings, can produce paths that loop back in time on paper. The problem is that these setups are extreme, and they may not be physically achievable. Even more important, they invite paradox. If the past can be changed, then cause and effect become tangled. Many physicists suspect the universe has a built-in protection, sometimes called chronology protection, that prevents closed time loops from forming. Quantum effects might destabilize any would-be time machine, or the required energy conditions might never arise in nature. It is a wonderful mystery because it is a question about consistency. Does the universe allow contradictions, or does it quietly refuse to let them start? Quantum theory and gravity disagree, and the universe keeps the peace. Quantum physics rules the small, and it describes particles as probabilities and fields as fluctuations. Gravity rules the large, and it describes space-time as a smooth geometry shaped by mass and energy. Each theory works brilliantly in its own territory. The conflict appears when both should matter at once, like the center of a black hole or the earliest instance of the universe. There, quantum uncertainty and intense gravity collide, and our equations stop agreeing with each other. We do not yet have a complete theory of quantum gravity, a framework that merges the two without contradiction. Many approaches exist, including string theory, loop quantum gravity, and others, but none has delivered decisive experimental proof. That leaves a strange piece in practice. The universe behaves consistently, and yet our descriptions come in two languages that do not fully translate. The mystery is not whether reality works. It clearly does. The mystery is what deeper set of rules allows both the quantum and the cosmic to be true at once. Dark matter might be particles, or it might be something stranger. The evidence for unseen mass is strong, but the identity of that mass remains open. A popular idea is that dark matter is made of new particles that rarely interact with ordinary atoms. Candidates include WIMP, actions, and other proposed species, each with different properties and search strategies. Experiments deep underground listen for rare collisions, while telescopes watch for telltale signals in space. Yet the lack of a clear detection has encouraged wider thinking. Perhaps dark matter is not a particle at all. Some ideas modify gravity itself, changing how it behaves at very low accelerations. Other ideas imagine hidden sectors, entire families of particles that interact with us mainly through gravity. There are even proposals where dark matter forms compact objects, like primordial black holes, though constraints are tight. The mystery is exciting, because the answer will reshape physics. Dark matter is not a small detail. It is the scaffolding of galaxies, and we still do not know what it is made of. Some theories suggest dark matter is made of tiny hidden clumps. If dark matter is made of particles, it might not be smoothly spread out. Gravity would make it gather into halos, and within those halos, it could form smaller substructures, like invisible satellite clumps. These clumps would not shine, but they could reveal themselves through gravity. One clue would be slight distortions in gravitational lensing, where a background galaxy's light is bent in a way that hints at extra small masses along the path. Another clue could come from the motions of stars in dwarf galaxies, which may feel the pull of substructure. Even stellar streams in our own galaxy, long ribbons of stars torn from clusters, can show gaps and wiggles if an invisible clump passed through. The idea matters because it could tell us what kind of particle dark matter is. Warm dark matter would erase small clumps, while cold dark matter would allow them. In that way, the smallest structures may carry the biggest answers. Dark energy could be a field or a flaw in gravity. The accelerating expansion of the universe is often described as dark energy, but that name is a placeholder, not a solution. One possibility is that empty space has an energy density that stays constant as the universe expands, sometimes linked to the cosmological constant. Another possibility is a dynamic field that changes slowly over time, which could make acceleration vary across cosmic history. There is also a more radical option. Perhaps gravity itself behaves differently on the largest scales, so the equations that work in the solar system are not the whole story for the universe. Each explanation has different fingerprints. A constant energy changes expansion in one way. A field can leave subtle patterns in how structures grow. Modified gravity can change how galaxies cluster and how light bends. Observations are improving, but the differences are subtle, and the universe is messy. The mystery is not just about acceleration. It is about what space is, and whether gravity is exactly what we think it is. The Hubble constant disagrees with itself, depending on how we measure. There are two main ways to measure the expansion rate today. One starts nearby, using distance ladders built from objects like Cephid stars and Type Ia supernova. It measures the universe as it is now, step by step. The other starts far away, using the cosmic microwave background to infer the expansion rate from the early universe and a cosmological model, then evolving that model forward. These methods should match. They do not, at least not perfectly, and the gap has persisted as measurements have improved. That tension could mean hidden systematic errors, like subtle calibration issues or unrecognized biases. It could also mean new physics, such as additional particles in the early universe or changes in how energy behaved long ago. Researchers are bringing in independent checks, including gravitational lens time delays and standard sirens from gravitational waves. The mystery is compelling because it sits at the intersection of precision and surprise. Either our measurements are missing something, or the universe is. The lithium problem hints our early universe recipe may be incomplete. Big Bang nucleosynthesis predicts how the first light elements formed in the first minutes, before stars existed. Those predictions match observations well for hydrogen and helium, and they do reasonably well for deuterium. Lithium is the awkward exception. The simplest models tend to predict more lithium than we observe in the oldest stars. That mismatch has been stubborn, which makes it interesting. The solution could be astrophysical. Perhaps lithium is destroyed or hidden inside stars in ways we do not fully model, especially over billions of years. Or the solution could be cosmological. Perhaps the early universe had additional processes, like decays of exotic particles that altered element production. Even small changes in particle physics can shift the outcome, because the early universe was a delicate chemical factory. The lithium problem is a small element with a big implication. It suggests we have either misunderstood ancient stars or missed a detail in the universe's first chemistry. Matter and energy may come in hidden forms, beyond our detectors. Physics has a history of discovering invisible ingredients by their effects. We found neutrinos because energy seemed to vanish in radioactive decay. We inferred dark matter because galaxies move as if extra mass is present. In the same spirit, there may be additional fields or particles that rarely interact with the forces we use to detect things. Some might couple only weakly to light, or only through gravity. Others might exist at energies we have not reached in accelerators, or in environments we cannot reproduce on Earth. Hidden components could influence how the early universe expanded, how structures formed, or how stars evolve. They could also show up as subtle anomalies in precision experiments, like unexpected shifts in particle decays or tiny deviations in fundamental Bacher constants. The challenge is that the universe offers many places to hide. Absence of evidence is not evidence of absence, but it is a narrowing map. Each new constraint closes doors, and each unexplained hint opens another. The mystery keeps the frontier alive because it asks a simple question. Have we met all the actors on nature's stage? The vacuum of space may seethe with temporary particles. In quantum field theory, what we call empty space is not a static void. Fields exist everywhere, and they can fluctuate even when no particles are present. These fluctuations are not directly visible, but their effects can be measured. The Casimir effect, for instance, shows that two closely spaced metal plates feel a tiny attraction, as if the vacuum has pressure that changes with geometry. On cosmic scales, vacuum behavior may matter even more. If space has an inherent energy, it could contribute to cosmic acceleration. If vacuum fluctuations influenced the early universe, they could have seeded structure by providing the initial irregularities that gravity later amplified. The vacuum also raises deep questions about what is real. If nothing has measurable properties, then emptiness is a kind of physical medium with rules and limits. The mystery is that the most familiar backdrop of existence may be an active participant. Space, even when it looks empty, may be doing quiet work in the background. The cosmic web links galaxies in filaments we cannot fully map. On the largest scales, galaxies are not sprinkled evenly. They gather along immense strands of matter, with wide, emptier regions in between. This structure is called the cosmic web, and it looks like a three-dimensional lacework stretched across billions of light years. We can trace parts of it by counting galaxies, but much of the web is made of faint gas and unseen mass that does not glow brightly. Some filaments are hinted at when background light passes through them and picks up subtle absorption fingerprints. Others show up when hot gas gently distorts ancient microwave light as it travels toward us. Mapping the web is like trying to sketch a forest at night, using only the way it blocks distant headlights. Still, the web matters because it guides how galaxies grow and where they get their fuel. It is the universe's scaffolding, and we are still learning its full shape. Galaxies appear aligned strangely in places, and it may be chance. In a universe built from randomness and gravity, you still expect patterns, but not patterns that look coordinated across great distances. Yet astronomers have found cases where galaxy spins, shapes, or orientations seem to line up more than simple statistics would suggest. Sometimes it happens within a cluster, where shared history could naturally align motions. More puzzling are reports of alignments that stretch across larger regions, where direct interaction seems unlikely. The hard part is separating a real cosmic signal from the many ways humans can be fooled by data. Surveys have selection effects, measurement uncertainties, and complex biases in how galaxies are detected and classified. Even a small bias can mimic an alignment when you have large catalogs. Researchers test this by using independent surveys, different analysis methods, and simulated universes that include known systematics. If the alignments persist, they could hint at early universe conditions or large-scale tidal fields. If they fade, they become a lesson in humility and careful inference. Some galaxy clusters seem to collide too fast for simple models. Galaxy clusters are the heaviest band structures we know, and when two of them approach each other, the encounter becomes a slow-motion catastrophe. Galaxies mostly pass through, but the hot gas between them can slam together, shock, and heat to tens of millions of degrees. By measuring shock fronts and the separation between gas and gravitational mass, astronomers can reconstruct collision speeds. In a few famous cases, the inferred speeds have looked uncomfortably high compared with what straightforward simulations predict for a universe like ours. That has sparked debate. Are the speeds overestimated because the geometry is trickier than it appears? Are we catching rare events at rare angles? Or does it hint that some assumptions about structure growth need adjusting? These collisions are cosmic laboratories. They test how gravity gathers matter, how gas behaves under extreme pressure, and how unseen mass moves when the largest objects in the universe crash. Gravitational lensing lets us weigh the invisible, like cosmic X-rays. When light from a distant galaxy passes near a massive object, the path bends. The result can be dramatic arcs, multiple images of the same source, or a subtle stretching that is only visible when you average many background galaxies together. This bending is gravitational lensing, and it turns the universe into a natural measuring device. The beauty is that lensing responds to total mass, not just the part that shines. That means you can map the distribution of mass in a galaxy cluster even when much of it is dark. Strong lensing reveals concentrated cores through bright arcs. Weak lensing reveals broader halos through faint statistical distortions. With careful modeling, astronomers can build mass maps that look like weather charts for gravity. Lensing also finds otherwise hidden galaxies by magnifying them, letting us study the early universe in more detail. It is one of the rare techniques that makes the invisible measurable, using light that was already on its way to us. We still debate how the first stars ignited in the dark. Before the first stars, the universe was filled mostly with hydrogen and helium, with no heavier elements to help gas cool. Pooling matters because heat resists collapse. So the earliest stars had to form under tougher conditions than stars today. Many models suggest the first stars were unusually massive because large clumps of gas could collapse without fragmenting into many small pieces. If that is true, these stars would have burned hot and fast, producing intense ultraviolet light and ending in violent deaths that seeded space with the first heavier elements. Yet we have never seen a true first-generation star directly, and their signatures must be inferred from later clues. Astronomers search for extremely metal-poor stars in our own galaxy, since their chemistry may preserve the imprint of the first explosions. They also search for indirect signals in distant galaxies and in the glow of the early universe. The mystery is about beginnings. It asks how darkness first learned to shine. Reionization changed the universe's fog, and its details are still unfolding. After the universe cooled, neutral hydrogen filled space and easily absorbed certain kinds of light. In effect, the cosmos was foggy to ultraviolet radiation. Then the first luminous objects turned on, and their energetic photons began stripping electrons from hydrogen again. This era is called reionization, and it was a phase transition for the universe. It changed how light could travel, and it altered how gas behaved around young galaxies. The big questions are about timing and responsibility. Did early stars do most of the work? Did small galaxies contribute more than rare bright ones? Did black hole activity play a role? Observations offer hints. The spectra of very distant quasars show absorption patterns that change with redshift, which suggests the fog cleared gradually. Measurements of the cosmic microwave background also carry integrated information about free electrons along the line of sight. New telescopes are now finding galaxies deep in this era, and their properties are helping us reconstruct how the fog lifted. It is history written in photons, and we are still learning to read it. There may be planets around dead stars surviving the apocalypse. When a sun-like star runs out of fuel, it swells into a red giant, and later sheds its outer layers, leaving behind a white dwarf. That process can be brutal for nearby planets, and it can destabilize orbits. yet evidence suggests some planetary material survives. Astronomers have found white dwarfs whose atmospheres contain heavy elements that should sink quickly, which implies ongoing accretion of rocky debris. In some cases, dust disks have been seen circling these dead stars, likely made from asteroids or fragments torn apart by tidal forces. This is a haunting scene. A star has ended, and the leftovers of a planetary system continue to orbit, collide, and sometimes fall inward. It also gives us a glimpse of our own far future, because the Sun will one day become a white dwarf. The mystery is which worlds survive intact, which are destroyed, and how often new stable configurations emerge after the chaos. Pulsar planets exist, and their origin story is wonderfully bizarre. The first confirmed exoplanets were not found around a sun-like star. They were found around a pulsar, a rapidly spinning neutron star that emits beams like a lighthouse. Planets there seem almost impossible at first glance, because the supernova that created the pulsar should have blasted nearby material with lethal energy. So how can planets exist in that neighborhood? One idea is survival. A planet far enough away might endure the explosion and remain bound. Another idea is rebirth. After the supernova, a disk of debris could form around the pulsar, and planets could assemble from that wreckage, like new worlds built from ashes. Pulsar timing is so precise that even small planets can be detected through tiny wobbles in the pulse arrival times, which is how these were found. Their existence expands our sense of where planets can be and how strange their formation pathways might be. They are reminders that nature does not always follow the most comfortable script. Interstellar dust can make new worlds and also hide them. Dust sounds trivial, but in space, it is a powerful ingredient. These tiny grains are often made of carbon-rich material, silicates and ices, and they provide surfaces where molecules can form more easily than in, quote, open gas. In cold clouds, dust helps build complex compounds by giving atoms a place to meet and stick. Dust also blocks and scatters visible light, which is why many star-forming regions look like dark gaps in the Milky Way. That hiding effect is frustrating, but it is also revealing, because it pushes us to use infrared and radio astronomy to see what is happening inside. In young systems, dust grains collide and clump, growing from smoke-sized particles into pebbles, then into planetesimals that can become planets. Dust is both curtain and construction material. It obscures, it cools, it catalyzes, and it builds. The mystery is in the details of growth. We can watch disks around young stars, but the jump from grains to planets is still a story with missing pages. The first galaxies may have been small, yet astonishingly bright. In the early universe, galaxies had less time to assemble, but they may have formed stars at a furious pace. Some early candidates look compact, with intense light pouring from relatively small volumes. That brightness could come from rapid bursts of star formation, from unusually massive stars, or from low dust content that lets ultraviolet light escape more easily. It could also reflect different stellar populations than we see nearby today, with hotter stars contributing more blue light. Another possibility is that early galaxies were fed efficiently by cold streams of gas, providing steady fuel even while the universe was young. The challenge is interpretation. At extreme distances, light is stretched to longer wavelengths, and measurements depend on careful modeling of spectra and dust. As data improves, astronomers can separate starlight from other contributions and estimate ages, masses, and star formation rates more reliably. These first galaxies matter because they help transform the universe's environment and because they tell us how quickly order can emerge from cosmic beginnings. Some exoplanets have comet-like tails, losing their atmospheres to space. Some worlds orbit so close to their stars that their surfaces and skies are being stripped away. Intense starlight heats the upper atmosphere until atoms and molecules escape, flowing outward like steam from a kettle. In extreme cases, dust can be dragged along too, creating a trailing tail that can stretch for huge distances behind the planet. When such a planet passes in front of its star, the tail can make the dip in starlight look lopsided, with a slow fade in or a lingering recovery. That strange transit shape is one way we infer the tail's presence. This is planetary erosion in real time. Over long spans, a once substantial world could be carved down, perhaps leaving a dense core behind. It also teaches us what starlight can do to a planet's chemistry. A tail is not just a visual. It is a record of a world shedding itself, atom by atom, into interplanetary space. A few planets orbit in ours, skimming dangerously close to their stars. Some planets whip around their stars so quickly that a year lasts less than a day. These ultra-short period worlds circle at distances where tides are fierce and temperatures can climb high enough to melt rock. They may be locked, with one side facing the star constantly, creating a permanent day hemisphere and a contrasting night side. Close orbits also raise the risk of gradual orbital decay, where tidal interactions drain energy and draw the planet inward over time. Many of these worlds are likely rocky and dense because fluffier planets would be puffed up and stripped by radiation. Their surfaces may host magma seas, and their thin atmospheres could be made from vaporized minerals rather than water and nitrogen. Detecting them is surprisingly efficient because they transit often, giving repeated chances to measure the same signal. The mystery is how they got there. Did they form close in or migrate inward from farther out? Each one is a reminder that planetary systems can produce worlds that seem to live on the edge of destruction. Some worlds may rain iron, driven by night-side condensation. On certain extremely hot giant planets, the day side can become hot enough to keep metals in gas form. Winds then carry that metal-rich air toward the cooler night side, where temperatures drop just enough for the vapor to condense into droplets. In that scenario, the planet could host rain made of iron, and perhaps other minerals, falling through an atmosphere that is nothing like Earth's. This is not a poetic metaphor. It is a straightforward consequence of chemistry under heat, plus powerful winds on a tidally locked world. The cycle would resemble a bizarre water cycle, but with metals and rocks playing the starring roles. Observations cannot see the raindrops directly, yet they can hint at these processes through phase curves that track how the planet's brightness changes with orbit, and through spectral signatures that suggest certain elements disappear where condensation is expected. These worlds are laboratories for weather at the edge of what matter can do. They show that in the right environment, even iron can behave like a cloud. Exoplanet atmospheres can be measured, yet clouds confuse the signals. When a planet transits its star, a thin ring of starlight filters through the planet's atmosphere. Molecules in that atmosphere absorb specific wavelengths, leaving faint fingerprints in the spectrum. This technique has revealed gases like sodium, carbon monoxide, and water vapor in some worlds. The difficulty is that clouds and hazes can mask the fingerprints. A high-altitude haze can flatten the spectrum, making an atmosphere look featureless even when it is chemically rich. Different cloud compositions can also mimic each other, which makes interpretation tricky. Some clouds may be made of silicates or metal compounds, especially on hot planets, while cooler planets may have different condensates. Researchers address this by observing at multiple wavelengths, including infrared where some gases have stronger features, and by comparing repeated transits to reduce noise. The mystery is not whether atmospheres exist. It is how to see through their disguises. A cloud layer can turn a clear chemical story into a blurred silhouette, and teasing it apart is one of the most active puzzles in exoplanet science. We have found water vapor on distant worlds, but not oceans. Water vapor is one of the first molecules astronomers look for, because it leaves strong spectral features and because it matters for climate. It has been detected in the atmospheres of a range of exoplanets, from hot giants to smaller worlds that sit closer to the realm of rocky planets. Yet an atmosphere with water vapor is not the same as a planet with oceans. A very hot world can have steam without liquid water, and a dry world can show vapor in only a thin layer or in localized regions. Clouds can complicate things further, hiding deeper layers where conditions might be different. To argue for oceans, scientists need more context. They look at temperature, pressure, atmospheric composition, and how energy moves across the planet. They also search for signs of weather, like changing cloud patterns or day-to-night transport. The mystery is that oceans are a surface feature, while most of our measurements are atmospheric hints. We are learning to read those hints more carefully, and each detection brings us closer to knowing which distant worlds truly have seas. The search for technosignatures is young and full of open questions. If another civilization exists, it might leave detectable traces that are not biological, but technological. Radio signals are the classic example, since narrowband transmissions can stand out from natural noise. Yet radio is only one possibility. Lasers could appear as brief optical flashes. Industrial chemistry might alter an atmosphere in distinctive ways. Large-scale engineering, if it existed, could reshape starlight in measurable patterns. The difficulty is choosing what to search for without assuming aliens behave like humans. Another challenge is separating artificial signals from natural and human-made interference. The field is learning to use machine learning to sift large data sets and to coordinate observations across multiple telescopes so that a candidate can be checked quickly. The search is also becoming more systematic, moving from a few targeted stars to wide surveys of the sky. The mystery is not only whether anyone is out there, it is also what would count as evidence and how we would recognize it when it arrives. In that uncertainty, the search feels like a new kind of exploration. Our probes will drift between stars, carrying human fingerprints quietly. A few human-made spacecraft are already on trajectories that will carry them beyond the outer planets, beyond the Sun's main influence, and eventually into our interstellar space. They will not arrive at a nearby star anytime soon, but over vast spans, they will pass through the galaxy as small artifacts of our species. Some of these probes carry intentional messages, such as the Voyager Golden Records, designed as time capsules that describe Earth through sounds, images, and basic scientific ideas. Even without such records, the probes themselves are signatures, built from metals and electronics that do not form naturally in that arrangement. In a sense, they are our first physical presence beyond the solar system, and they will likely outlast many things on Earth. The long drift also raises a quiet question about contact. If another civilization ever finds them, it will be because curiosity is universal. The probes are slow, silent ambassadors, and their journey is both modest and profound. The edge of the observable universe is not an edge at all. There is a limit to what we can see, not because the universe ends there, but because light takes time to travel. Beyond a certain distance, light has simply not had enough time to reach us since the universe began. That boundary is called the observable universe, and it expands as time passes, revealing more regions as their light arrives. Yet there are also areas we may never see, because space itself is expanding. If expansion carries regions away fast enough, their light may never catch up to us. This creates a horizon that feels like an edge, but it is really a limit of communication, not a wall. It is like standing in fog and saying the world ends where visibility fades. The world continues. We just cannot see it. The mystery is that reality almost certainly extends beyond our cosmic view, and we must build our understanding with a map that is inherently incomplete. Space expands everywhere, yet gravity still gathers islands of matter. Cosmic expansion is often misunderstood as an outward blast. It is better thought of as the stretching of space on large scales, which increases the distance between faraway galaxies over time. Yet gravity is still at work, pulling matter into bound structures. That is why galaxies, clusters, and our own local group can remain intact even while the broader universe expands. On small scales, the gravitational glue is strong enough to overcome the gentle stretching. On large scales, expansion wins, and distant galaxies drift away. This creates a universe that is both dispersing and clustering, depending on where you look. The result is a kind of cosmic geography, with dense archipelagos of matter separated by vast growing distances. Understanding this balance is crucial for predicting the universe's future and for interpreting what we see in deep surveys. It also carries a philosophical weight. The universe is not choosing one story. It is telling two at once: separation and gathering, expansion and structure, a tension that makes the cosmos feel alive. The universe's future could freeze, rip apart, or recycle. Cosmology is unusual because it lets you ask a question that sounds like mythology, yet it can be tackled with data. How will everything end? The answer depends on what dark energy really is, and whether its strength changes with time. If expansion continues and matter thins out, galaxies will drift farther apart, and star formation will slow, leaving a colder, darker cosmos. If the driving force of expansion grows stronger, it could eventually overwhelm gravity and tear structures apart. And if dark energy changes sign, or if new physics appears, the universe could slow, stop, and perhaps collapse into a new beginning. Each option is a different ending to the same story, and all are being tested by measuring how expansion behaves across cosmic history. The future is not only far away, it is a clue about the laws that run the present. Some models predict a big rip where even atoms come undone. In the Big Rip picture, dark energy does not stay steady. It strengthens as time passes. At first, that would be hard to notice, because local gravity would still hold galaxies together. Later, the expansion would become more forceful. Galaxy groups would separate, then galaxies themselves would be pulled apart. Eventually, even solar systems would be disrupted, as the stretching of space overwhelms the forces that keep planets in orbit. The most unsettling step comes last. If the runaway continues, molecules and atoms could be torn apart as the expansion wins over the forces inside matter. This is an extreme scenario, and it is not the leading expectation, but it remains mathematically possible for certain kinds of dark energy. What makes it fascinating is its structure. It turns the end of the universe into a timetable of disassembly, moving from the grandest scales down to the smallest. By measuring how dark energy behaves now, we are quietly checking whether such a fate is even on the table. Other models predict heat death, a slow fading into calm darkness. Heat death is not a dramatic explosion. It is a gradual quieting. Over immense spans, stars burn through their fuel, and the gas needed to make new stars becomes locked away in dim remnants or scattered too thin to gather. The universe keeps expanding, so distant galaxies slip beyond reach, and each local region becomes more isolated. Energy differences even out. Hot things cool. Useful gradients fade. In that far future, the cosmos approaches a state of maximum entropy, where change still happens, but the grand, organized fireworks become rare. This idea can feel bleak, yet it is also strangely serene, like a universe exhaling and settling. It is grounded in thermodynamics, and it fits naturally with a universe that expands forever. The mystery is not the concept. The mystery is whether dark energy will truly remain steady long enough for this slow ending to unfold. Our measurements of expansion are, in a way, measurements of how patient the universe might be. A cyclic universe is possible, though evidence remains elusive. A cyclic universe offers an ending that is also a beginning. Instead of one big bang followed by endless expansion, the cosmos could pass through repeated phases, expanding, cooling, then somehow contracting or resetting into Ca. Another hot start. There are many ways to imagine this in physics. Some involve a bounce that avoids a singular collapse. Others involve branes or extra dimensions, where cycles are driven by dynamics beyond ordinary space. The appeal is obvious. It sidesteps the question of a single absolute beginning and offers a rhythm to cosmic history. The difficulty is survival of evidence. Each cycle could erase the detailed record of the previous one, leaving only faint traces in primordial patterns or in the distribution of large-scale structure. Scientists look for signatures that would be hard to mimic in simpler models, such as certain imprints in the spectrum of early universe fluctuations. So far, nothing has forced a cyclic conclusion. Yet the idea persists because it is a serious attempt to make cosmology feel complete, with no first page missing. The multiverse is a serious idea, yet it is hard to test. The multiverse is often treated like science fiction, but it grows naturally out of some scientific frameworks. Inflation, for example, can be imagined as a process that ends in some regions while continuing in others, creating many bubble universes with different conditions. Some versions of fundamental physics also allow many possible vacuum states, like different valleys in a landscape of laws. If our universe is one valley among many, then some features we measure could be local facts rather than universal necessities. The challenge is evidence. Other universes, if they exist, may be causally disconnected from us, which means no light, no particles, no direct messages. Researchers have proposed indirect tests, such as searching for scars from ancient bubble collisions in the cosmic microwave background. Those searches have not delivered decisive proof. The multiverse remains a bold idea with a frustrating barrier. It might be true and still remain difficult to confirm. That tension is part of what makes it a mystery worth treating carefully, with both imagination and restraint. Cosmic coincidences appear everywhere, and we argue over their meaning. Sometimes the universe seems to set its knobs to strangely convenient values. Certain ratios and scales line up in ways that make scientists pause. Why is the density of dark energy so small compared with what naive quantum estimates suggest? Why do the amounts of dark matter and ordinary matter end up within a couple of orders of magnitude of each other, when they could have been wildly different? Why do some dimensionless constants sit in ranges that allow long-lived stars and complex chemistry? These are called coincidences, and they split opinion. Some researchers expect deeper physical principles will explain them, like hidden symmetries or undiscovered fields. Others suggest we observe these values because only certain ranges permit observers at all, which turns the question into one of selection. The debate is intense because it touches both physics and philosophy, and because it influences what kinds of theories are considered promising. Coincidences are not proof of anything by themselves. They are signposts that say, look here. Something might be missing from the story. Life might hide underground on worlds that look dead from space. A planet can appear barren at the surface and still be active below. Underground environments are sheltered from radiation, temperature swings, and impacts. On Earth, microbes live deep in rock, feeding on chemical energy rather than sunlight. That expands the imagination for other worlds. Mars, for instance, is cold and dry on the surface today, but underground it could preserve pockets of ice, brines, or reactive minerals that provide energy. Icy moons offer an even stronger version, with water oceans hidden beneath shells of ice. Even a world with a thin atmosphere could harbor life below a few meters of soil, where conditions are steadier. The challenge is access. Remote sensing is good at surfaces and atmospheres, but underground life is shy. You need landers, drills, or clever ways to sample material that naturally rises up, like plumes or fresh impact ejecta. The mystery is not only where life could be, it is how often it chooses to hide, turning a seemingly quiet world into a secret habitat. We do not know how common habitable moons might be. Moons are easy to overlook, yet they could be plentiful places for life. A large moon orbiting a giant planet could receive energy from several sources. Starlight, reflected light from the planet, and tidal heating from gravity flexing can all contribute. That means a moon might stay warm enough for liquid water, even when the planet is far from its star. A thick atmosphere could help, and so could an internal ocean beneath ice. The ingredients for habitability are not limited to planets, but moons are harder to detect around other stars. Their signals can be subtle, appearing as small timing shifts or extra dips in starlight during a planetary transit. Even when a candidate is suggested, confirmation is difficult. Meanwhile, our own solar system hints at possibilities. Multiple moons show signs of hidden oceans, and they exist in very different environments. If moons can be habitable here, they could be common elsewhere. The mystery is how many exist, and how many stay stable for long enough to let chemistry grow into biology. The simplest question remains open. Why is there something at all? Physics can describe how the universe evolved from a hot, early state into galaxies, stars, and planets. It can even propose mechanisms for how a universe might arise from quantum conditions. Yet beneath those explanations sits a question that refuses to go away. Why does anything exist rather than nothing? Some approaches suggest that nothing is not stable, and that quantum laws naturally produce fluctuations that can become worlds. Others argue that the question is misplaced because the universe could be a necessary consequence of deeper mathematics. There are also views that treat existence as a brute fact, with no further explanation available. What makes this question so powerful is that it lives at the intersection of science and meaning, and it can be asked without any specialized training. It is the childlike question that survives every textbook. In a sleepy science mood, it becomes less of a demand for an answer and more of a wide-open doorway. The mystery itself can feel like a kind of awe. Every new telescope finds new puzzles, and the cosmos stays ahead. Astronomy has a pattern. Build a better instrument, and the universe rewards you with surprises. Radio astronomy revealed pulsars and strange bursts. X-ray telescopes uncovered violent high-energy skies. Precision surveys mapped dark matter through lensing and charted planets around other stars. Each leap in sensitivity expands not only what we can measure, but what can be unexpected. A new telescope does not just fill in missing details. It often reveals entirely new categories of objects, or behaviors we did not predict, or tensions between measurements that force theories to adapt. This is not a failure of science. It is how science grows, by being confronted with reality at higher resolution. The cosmos stays ahead because it is bigger than our current imagination, and because we are always sampling it with incomplete tools. That is a hopeful kind of mystery. It means there will always be more to learn, more to wonder at, and more reasons to look up. When you listen to space mysteries, you are listening to a frontier that keeps renewing itself. As we come to the end of our journey through space mysteries, you might notice how wide the universe feels and how softly it holds its unanswered questions. We drifted past the invisible weight of dark matter and the strange push of dark energy. We listened to space-time ring like a distant bell after black holes collided, and we wondered what lies behind a horizon that never gives anything back. We visited storms shaped like geometry on Saturn and watched Jupiter's ancient red whirlpool slowly change with time. We traced the hidden rivers of Titan, the salt-bright plumes of Enceladus, and the quiet possibility of oceans sealed under ice on worlds that never see warm sunlight. We followed the ghostly paths of neutrinos, the sudden flare of magnetars, and the brief, haunting whisper of a signal that appeared once and never returned. And through it all, the biggest mystery stayed close. The cosmos keeps offering clues, but it never rushes, and it never tells the full story at once. If you enjoyed this sleepy voyage, you could support the channel by liking, subscribing, or leaving a calm little comment before you rest. It helps more curious minds find their way here. And if you are still awake, there is another video waiting on your screen, ready to carry you onward into another corner of science. But for now, let the questions loosen their grip. Let your shoulders soften. Let your jaw unclench. Allow your breathing to slow, steady, and deepen. Picture the night sky as a dark ocean above you, vast and patient, with every star a small, steady light. You do not need answers tonight. You only need rest. Sleep well, and good night.